For generations, we've stared up at the night sky and asked if anyone else is out there. We usually imagine the answer arriving in a single world-changing moment, a sudden radio signal cutting through the static, or a clear image of a distant world. But the actual hunt for extraterrestrial life is unfolding right now across two entirely different, deeply contrasting fronts. The first is the outward search, a series of meticulously planned, highly funded scientific missions peering billions of light-years into deep space. The second is the inward search. This is urgent, unpredictable, and defined by chaotic military encounters with unidentified objects flying directly through our own airspace. The modern hunt for extraterrestrial life requires reconciling these extremes, the pursuit of perfect data from light-years away, and the struggle to make sense of the chaotic evidence gathered right in front of us. NASA's current astrobiology strategy focuses on the active detection of chemical fingerprints, searching for signs of microbial life and atmospheric activity on distant worlds. Executing this requires extreme interagency coordination and decades of careful engineering to build dedicated, specialized observatories. The gold standard for this outward search is a technique called transit spectroscopy. When an exoplanet crosses in front of its host star, a tiny fraction of that starlight passes through the planet's atmosphere before it reaches our telescopes. This diagram illustrates how scientists break that filtered starlight down into a readable graph. The distinct dips you see here correspond to specific wavelengths of light absorbed by the planet's atmosphere. Those missing wavelengths are chemical fingerprints. They indicate the potential presence of biosignatures like methane or oxygen, or perhaps even technosignatures from advanced civilizations. The outward search produces highly calibrated, peer-reviewed data. It is a methodical process built entirely to answer a biological and philosophical question. Back on Earth, the inward search looks entirely different. Since 2004, aviators on operational military flights have been reporting unidentified anomalous phenomena, or UAPs, exhibiting highly unusual flight characteristics. The problem lies in the equipment. Fighter jet radars and infrared cameras are designed solely to target known enemy aircraft. They are not scientific instruments built to study anomalous physics, which leaves them struggling to track these erratic signatures. Compounding this technical limit is a severe cultural barrier. For decades, a deep-seated stigma and the fear of career damage have prevented commercial and military pilots from officially reporting what they see. That began to shift with a preliminary assessment from the Office of the Director of National Intelligence. This report created a mandate to finally categorize these messy, stigmatized encounters. The ODNI established 5 specific categories to filter these events: airborne clutter, natural atmospheric phenomena, classified U.S. developmental programs, foreign adversary systems, and a catch-all bucket for other. Unlike the outward search for biology, this inward search is a high-stakes matter of flight safety and national security, driven heavily by the concern that terrestrial adversaries might have achieved breakthrough technology. Currently, the UAP investigation is held back by the lack of a standardized civilian reporting system. The data we do have is sparse, anecdotal, and ultimately too noisy for serious analysis. To fix this, NASA has been called in to assist the intelligence community. The goal is to take the rigorous scientific frameworks used in deep space exploration and apply them directly to our own atmosphere. NASA plans to leverage existing, non-punitive frameworks like the Aviation Safety Reporting System. This allows commercial pilots to submit their observations safely, without stigma, so that scattered reports can be funneled into a centralized database. This graph illustrates the next step in that process. By gathering a vast amount of centralized data, machine learning algorithms can strip away the noise, separating recognized baseline patterns from genuine anomalies. Part of this initiative requires establishing exactly what normal phenomena look like on military sensors. Knowing the precise signature of a standard weather balloon, for example, is essential to eliminating false positives. This methodological upgrade forces us to improve our observational capabilities and data processing across the board. It effectively bridges the gap between national defense and astrophysics. Applying the same scientific rigor to our own airspace as we do to deep space ensures that whether the next discovery is an alien microbe or an advanced drone, we will have the verified data required to confirm it.